Transmission line equations. The purpose of this video is twofold. First, I'd like to introduce transmission lines, just talk about them for a bit. And then I want to get into deriving the transmission line equations and end this video with a derivation of the wave equations for voltage and current on a transmission line. The overall concept here is waveguides. In electromagnetics, a waveguide is any kind of a pipe that sort of confines and guides electromagnetic energy. And we can divide waveguides into two broad categories. One of those that I have labeled here as pipes is normally what people mean by waveguides. But usually a pipe, it has one metal or one hunk of dielectric that guides energy down that. The other half of this, which is really the focus of this next series of videos, is transmission lines. Transmission lines are waveguides, but a special class of waveguides. They have to have at least two conductors. Having two conductors, they can go all the way down to DC and conduct DC signals. There's really no low frequency cutoff. And when we talk about transmission lines, they tend to be much smaller than the pipe type waveguides compared to the wavelength. And so we really tend to think of these more as circuit elements or interconnects in our circuit. And they include things like coaxial cables, microstrip transmission lines, twisted pair for phone cables in the old days, and so on. So even though all of these different transmission lines look different, it turns out there's a framework that we can put these in to treat them all as the same. And so we'll derive the resistance and inductance and conductance and distributed capacitance and these types of parameters. And once we have those, we can treat all transmission lines the same. It's just deriving those from the transmission line that involves an electromagnetic analysis, and that's what differs between the transmission lines. Deriving those from the geometry of the transmission line, that's reserved for a later lecture. That's a more rigorous electromagnetic analysis. For this series of videos on transmission lines, we're going to assume that somehow magically we will know that distributed resistance, distributed inductance, distributed capacitance, and distributed conductance. So let's proceed. At its simplest, a transmission line is two pieces of wire. Well, we know that there's some resistivity in the wire, and if there's any sort of dielectric between the wires, there may be a small amount of conduction between that. And the two wires form somewhat of an inductor and somewhat of a capacitor, and we have all of these different RLC properties really uniformly distributed across this transmission line. And we can start to think of a transmission line as just this series parallel network of resistors, inductors, and capacitors. They're definitely not discrete components, but you'll see that we soon will treat it like discrete components, but they're smeared, smooth, distributed across the transmission line. Very difficult to visualize, and this is really the best I've done at trying to convey that point. So if we look at a tiny piece of transmission line of some length that we're calling delta Z, we can write a simple little circuit that has a series resistor, a series inductor, a conductance, a resistance going from wire to wire, and also the capacitance from wire to wire. So this is a simple RLGC circuit model. There's many other options for circuit models for transmission lines. This is very common and a very simple one. And I think it's easier to sort of get physical insight with this type of model. So there's four circuit elements in it. And the first thing I want to point out is these are distributed circuit elements. So even though we're writing this as a discrete resistor, it actually has units of ohms per meter because it's distributed over the length of the line. So in order to treat this as a lumped element, we actually have to multiply by its dimension delta Z, and the delta Z is the length of this whole circuit model. So that resistor really is distributed over the entire transmission line. So this particular R is the series resistance, and that's mostly due to the resistivity in the conductors of the transmission line. Likewise, we have a distributed inductance with units of henries per meter. This is also smeared across or distributed across the entire transmission line. And this is because when we have current conducting in wires, those generate magnetic fields that stores magnetic energy, which can get released in the form of a current, and so inductance arises. So our transmission lines will always have some sort of distributed inductance. Usually transmission lines, they're separated by some kind of dielectric, and that dielectric is not perfect. That can partially conduct. And so we model that as a conductance G. Now, even though conductance is 1 divided by resistance, this conductance is not the reciprocal of the series resistance. These are representing two different things. R is more representing the resistance through the conductor. This G is more representing the resistance through the dielectric separating them. So don't think that G is calculated as 1 over R. They are separate elements in the circuit. And again, this conductance is a distributed parameter over the whole length of the transmission line. And last, we have our distributed capacitance. Because we have at least 2 wires, so here we're showing 2 wires, that forms a capacitor. There's an electric field between those lines that stores electric energy that can get stored and released, and so we have distributed capacitance as well. So we're describing our transmission line as having a distributed resistance, an inductance, conductance, and a capacitance. We can make a comparison between a transmission line and a wave in a homogeneous medium. And so the distributed inductance really takes the same role as the permeability when we talked about waves. The distributed capacitance takes the same role as permittivity, and this conductance parameter takes the same role as the conductivity. And you'll see how this analogy comes up, and we'll use it in subsequent videos. Just some examples of these different RLGC parameters for different transmission lines. We have the old RG59 coax cables that used to deliver television signals to our televisions. And notice we have a distributed resistance, 36 milliohms, distributed inductance, 430 nanohenries, conductance, 10 microohms, capacitance, 69 picofarads. Impedance is something we'll talk about later, but about 75 ohms. Now, I won't keep reading through all these numbers, but my point is, even though I'm showing very different types of transmission lines, notice these parameters are very consistent. And that's rather surprising, at least to me. So the distributed resistance always seems to fall around 100 milliohms per meter. The distributed inductance always seems to fall around several hundred nanohenries per meter. The distributed conductance is always on the order of a few microsiemens per meter. And distributed capacitance is usually, 50 to 100 picofarad per meter range. And it's just surprising to me that regardless of these different structures, that those parameters are very, very consistent. And they come together in different proportions to give us different impedances. And later we'll talk about things like attenuation and phase constant and these other parameters. And they can lead to different properties there as well. Transmission line equations. In the comparison between the circuit model and the wave model, Maxwell's equations lets us connect that. And remember way back when we were talking about Maxwell's equations, and we were looking at this line integral of the electric field, and we did that to calculate a voltage. Then when we were talking about Ampere's circuit law, we did a similar line integral of the magnetic field and got a current. And really, these two equations are showing us the connection between voltage and current and the electromagnetic fields. Now, on a transmission line, everything's confined, everything's defined. Really, signals can just go left and right. And so it makes much more sense to analyze things in terms of a voltage and current instead of an electric field and a magnetic field. We are still free to analyze things with an electric and magnetic field, but it's not necessary, and in this case, I think the analysis simplifies considerably, analyzing things in terms of voltage and current. So that's what we're going to do for our transmission lines. And we have scalar quantities, no more vector quantities. We're going to derive transmission line equations, and that's what we're showing to the right here. So we will derive these by looking at that circuit model and doing some circuit analysis on it. Making this comparison again from waves to signals on a transmission line, these transmission line equations take on the same role as Maxwell's curl equations did. We saw that Maxwell's curl equations really in and of themselves were not directly useful equations. We derived a bunch of stuff from them. We substituted one into the other, we got the wave equation, we solved that, and we built on that. And a similar thing will happen. These transmission line equations in and of themselves are not directly useful, at least not very often, but we will substitute one into the other, we'll get the wave equation, and everything falls out of those two equations. So let's go ahead and solve or figure out, derive those equations from our circuit model. So we start with our circuit model, and of course we have our distributed resistance, our distributed inductance, distributed conductance, distributed capacitance, and we're looking at one little tiny segment in our transmission line. And so it starts at position Z, and it ends at position Z plus delta Z, and eventually we will let this delta Z go to 0. So at the input of our little segment of the transmission line, we have a voltage, and we just call that V of Z at T. And at the output, we have another voltage. That is at Z plus delta Z. So the first thing we'll do is we will apply Kirchhoff's voltage law around the outer loop of the circuit. So this is the loop we're going to take. So let's go ahead and look at this one term at a time. So starting here, if we're writing Kirchhoff's voltage law, we're working upward. The first sign we see is a negative sign, so we write negative VZT, and that's our first element. If we keep going, now we cross our resistor, and the current through it will be some I at ZT. So the voltage across that resistor, we have a positive sign, the current times the resistance, which is R times delta Z. Then we encounter our inductor. So again, we add L dZ di dt. We just have a wire here. We keep going. Now we encounter the output voltage, and the first sign we come across is a positive. So we write positive V at Z plus delta T. And that essentially completes our loop. So that is Kirchhoff's voltage law written around the outer loop of the model we're using for our transmission line. So this top equation here is what we derived on the previous slide. All we're going to do is rearrange some things. Let's bring all of the voltage terms to the left side of the equation and all of the current terms to the right-hand side of the equation, and then divide the whole thing by delta Z. So that isolates delta Z to this point here. Now let's look at this term for a bit. V at Z plus delta T minus V of Z divided by delta Z. And if we go back to our calculus, what we'll see is that is the actual definition of the derivative of V in the limit as delta Z goes to 0. So that's exactly what we do. In the limit that delta Z goes to 0, this term on the left becomes a derivative. And in fact, it becomes a partial derivative because we have two independent variables, Z and T. So we're not allowed to write that as an ordinary derivative. That is our first transmission line equation. We're ready to derive our second transmission line equation. So we're back to our model for our transmission line. Instead of using Kirchhoff's voltage law now, we're going to write Kirchhoff's current law by summing the currents coming into this node. Well, previously we wrote the current on the left as IZT. So we include that term. Then on the right-hand side of the circuit, we have a current at Z plus delta Z leaving. And since it's leaving, it gets a negative sign. We have current leaving that node through the conductance term. Since it's leaving, we have a negative sign, and it's G delta Z times V at Z plus delta Z. That's the voltage across this conductance, our output voltage, if you will. One more current term. That's the current term leaving through that distributed capacitance. Since it's leaving, it gets a negative sign. And it's C delta Z, which is the lumped capacitance, times dV dt. And all of that equals 0. We have summed all of our currents entering that node in the circuit. So this top equation is what we derived on the previous slide. Then what I'm going to do is bring all of the current terms to the left and all of the voltage terms to the right. Now we look at this term. We have the definition of a derivative again in the limit as delta Z goes to 0. So that's exactly what we do. We let delta Z go to 0. That means these voltage terms reduce to just the voltage at Z. But this becomes a derivative. And again, a partial derivative because we have two independent variables. So we have the partial derivative of the current at ZT. That is our second transmission line equation. Transmission line wave equations. So we derived our transmission line equations in the time domain. What we'd like to do now is jump to the frequency domain. So we will Fourier transform our time domain transmission line equations. When we do that, we end up with these two equations. And so the Fourier transform of this term is just R times I. It really doesn't change a whole lot other than T becomes omega. But this term, we have a derivative with respect to time. So we end up getting L times j omega times this current. And that's the j omega down here. Our derivative on the left, that stays the same, but it becomes an ordinary derivative because we only have one independent variable now. It's only z. That time variable is now gone. And a very similar thing happens over here, and we get our second transmission line equation in the frequency domain. So our transmission line equations in the frequency domain are actually called the Telegrapher equations. And I'll mention again, these really are serving the same role as Maxwell's curl equations. In and of themselves, they're not really directly useful, but we will derive everything that is useful from them. So here's our two Telegrapher equations now. Let's derive a wave equation in terms of the voltage. To do that, the first thing we'll do is we'll take equation 1 and differentiate it with respect to z. So we get a second order derivative with respect to z on the left and a first order derivative with respect to z on the right. Now we have the derivative of the current on the right. Well, our second equation gives us an expression for the derivative of current. We can plug that into equation 3 to arrive at an equation just in terms of the voltage. And so that's exactly what we do. Rearrange terms a little bit, and we see that this is now a wave equation. So that's our first wave equation in terms of voltage. We can do this again to derive a wave equation in terms of the current instead of voltage. Let's go ahead and do that. So now we start with equation 2. We differentiate it with respect to z. So we get a second order derivative with respect to z on the left and a first order derivative with respect to z on the right. Well, our first equation gives us an expression for that first order derivative of z. So we can plug that expression in here. Now we have a differential equation just in terms of the current. And then we rearrange some things and we get something that looks like a wave equation, but now in terms of the current. So we're coming away with two wave equations now, one in terms of voltage and one in terms of the current. Notice in both of those wave equations we had this term involving our distributed circuit elements. So let's define a complex propagation constant, which we interpret the exact same way we did when we talked about waves. It has a real and an imaginary part, and it will turn out that the real part is attenuation, and the imaginary part is our phase constant describing oscillation. So we set that equal to the square root of these distributed terms. That lets us write our wave equations in terms of voltage and current this way, just in terms of gamma squared. And these differential equations are actually the same wave equations we had when we talked about waves in electromagnetics. So if we handed those equations off to a mathematician, and we didn't even have to tell the mathematician what they were, the mathematician could return the solutions to those. One solution for voltage, one solution for the current, and if we look at that, we see it's really the same solution, and that makes sense because it came from the same differential equation. Just like before, we can look at the sign in the exponential and see that when we have an e to the minus gamma z, we're talking about forward waves here. So we give these amplitude terms a plus superscript to remind us that those are the amplitude terms for the forward wave. Likewise, these other exponentials have an e to the positive gamma z. That's telling us these are backward waves. So we put the minus superscript on the amplitude terms to remind us that those are the amplitude terms for backward waves on the transmission line.